Hello everyone! In this video I'll be doing an example program that has a linked list in it. We're going to revisit our student record example that has this information about students, got last name, first name, and the numerical portion of the PID. And we're going to store those in our program using a linked list, using an add in order function so that there won't be any need for a sort function. So I've grabbed some things from the previous example, like the string library, standard input-output library. We know the number of students is 5, that's how many we have in our file. We're using max to control the maximum string length. Here's our structure from the previous one. We're going to turn this into a linked list, which is really easy. It's already got the data portion of the linked list node. What we need to add is the link portion, which is just going to be a pointer of the same type. So this is type struct record. So this is going to be a struct record pointer that we're going to call next. So the other thing that I've grabbed is this student compare function. That's the one that compares two students based on last names first, then first names, and then PID if they have the same last and first name. So we'll use that to build our insert in order function. So in main, we're going to have our list. It's going to be called student list that we're going to start as initially empty. And we're going to build some functions to interact with our list. And anything that modifies the list should return a pointer to the head of the list. So we're going to have get students, and we'll use that function to interact with the file. And we're also going to have an insert function, which is going to be responsible for inserting nodes created in get student into our list. So we're going to need both the head of the list and the new node to be inserted. Once we've built the list, we'll want to print it out. Before we leave the program, we'll want to remove all of the things that we've allocated space for. So we're going to make a copy of our delete from the end and our wrapper function delete all. So that we can empty our list before we exit out the program. Start with get students. We'll just copy our prototypes. Get students is going to read information from a file, create space for a new student record, and then call insert to add the student to the list. So this is the function that's going to be interacting with the file. So we're going to create our file pointer and open students.txt for read mode. That's the file that I have the student information in, students.txt. We'll have a counter because we need to do something with the file num students times. So there's 5 students, so we're going to iterate 5 times. And each time we're going to allocate space using this temp pointer so that we can allocate space for the student, get information from the file into our record, and then we'll add it on to our list. So first step is allocated space, which we use our malloc function for. We want something that is the size of struct record. which has two strings, first name, last name, PID, and now a pointer. So malloc will create enough space for one of those. And then we will structure the return type to be something of type struct record pointer. Then we can read information from the input file and store that in this space that we just created. So first is the last name, second is the first name, and third is the PID for each student. Because that's the same order that it is in the file. Last name, first name, PID. So we'll read string, string, integer, store it last name, first name, PID. And then we will add that to the list by calling the insert function with temp. We'll give ourselves also a default state for the link portion. So this is all of the data for the node. This is the link, which will default at null. It's possible that the insert function will change that based on the needs of the list, but just in case, it'll have an ending marker. And when we're done, we'll return the head of the list. So the purpose of insert is to do an add in order using new node. We're going to add that to head, and we'll use student compare to figure out how they should be ordered. So remember, there's a few things for us to check for. We're going to check to see if list is empty. We'll check to see if the new node belongs at the front of the list. We'll look for it somewhere in the middle. And if none of those apply, we'll add to end and finish by returning the head of the list. So in order to do that, we're going to need a helper to traverse the list, and then we can get started. So if our list is empty, then our new node is the only node in the list, so it's both the front and the back and the middle. Then we'll check the front of the list. We're going to use our student compare function. So this part can get a little confusing. What we have is head and new node, both of which are pointers to a struct record. And we're going to use student compare, which takes in not pointers, so just data types of type struct record. So in order to use this function, we're going to have to dereference the pieces of information that we're looking at. So we don't want new node. New node's a pointer. Instead, we want what new node is pointing at. So we'll dereference new node. We'll dereference head, pass those to student compare. And if it returns a value that is less than 0, then we know that our new node should be the front of the list. So we'll modify the link so that it points to the rest of the list stored in head and return that as the new front of the list. So if the list isn't empty and we're not adding to the front of the list, then we need to look for it somewhere in the middle. We're going to traverse the list as long as the next node in line is not null. and we're going to use student compare to find the predecessor of our current node. So we're going to compare, calling our student compare function, our current node with the node after helper. Because if we find out that new node should come before this one, then helper is the logical predecessor and helper next is the logical successor. So if we find that, we want our new node to point to the successor. And the logical predecessor, helper, to point to the new node. And then we're going to return the head of the list. We're using less than or equal to 0 just in case we get two records of the same type. We really shouldn't, but just in case, we'll go ahead and add them in the correct order. And we'll continue looking through the list until we find this location, or until we get to the end. So if we get to the end and we've not added anything to the list, meaning we haven't returned yet, then we'll go ahead and add on to the end, where helper next should be equal to the new node that we've created. And we can return the head of the list. Now to see all of our students, we're going to need to print them out. And remember, we don't want to move the pointer to the head of the list. That's why we keep creating helpers. So we'll create a helper to point to the head of the list. And as long as helper is not null, we can print the contents of the node helper, which is 2 strings and an integer. So that'll be helper, let's do last name, first name. Helper last name, helper first name, and helper PID. So we're going to get our student information from the file. We're going to add it to our list. We're going to print out the list. Now before we end our program, we're going to go ahead and make our delete functions so that any of the space that we've allocated we can then give back to the computer. And these are going to be very similar to the ones we did in the integer list example, where delete end deletes from the very end of the list, and delete all continually calls delete end until the list is empty. So inside delete end, we're going to create a helper that we can use. We're going to check to see if the list is already empty. If so, there is nothing for us to delete. We're going to check to see if there's only one node in the list. And if so, we can just free that node and return null. Otherwise, we'll need to look through the list to find the very last node. Then we can set temp equal to the very last node. We can change the links so that the list no longer sees that node, and then we can free that node. And now we can use this function to delete all of the nodes, as long as head is not equal to null. Delete something from the end of the list. Repeat until head is null, then return null because now the list is empty. So now that we've got all of our support functions, we're going to modify main. To make use of all of those functions, we'll call getStudents, which processes the information from the file and calls the insert function. We'll then print our students, our student list. And before we leave, we're going to delete all of our list so that all of that memory that we've allocated is freed back to the system. And we're just going to include this final check to make sure that the list got deleted before we exit the program. So now let's run it. We should see our 5 students, the same as the ones in our file, in alphabetical order by last name, with no sort function required. And it says at the end that the list is deleted, so that's all of our functions working together: get students, insert, print, delete, and delete all, to print our list of students in order and then free that memory back to the system at the end. So that's our linked list example using the student records. I hope you found it useful. I'll see you next time.